Alright guys, let's talk reflections. So just like with translations, you're going to see very similar format here. And again, please make sure that you're filling out the questions maybe as we go, or you do right afterwards, up to you. So again, this is designed to help kind of tie in the information we thought about in class to something maybe a little more practical, something that we can actually do. But again, the big picture here is the same. Ultimately, we're only talking about reflections because at some point, I'm going to ask you to prove stuff's congruent, and that's going to that's going to include being able to actually perform a reflection because you know it's not going to change the shape. So again, if you kind of felt lost a couple days ago, before the week, last week, uh, this is maybe an opportunity to get that information tied together. Anyway, so let's talk reflections. We're going to start in a familiar place. Let's talk about how we can notate, and identify a reflection. So let's start with the algebraic rule. Again, this is very middle school-ish. In fact, more so in this case because the rules I'm about to show you here make absolutely no sense except in a very specific context. But it's a really nice place to get started. So the algebraic rule xy goes to some other thing. That other thing I'm talking about could be a lot of different possibilities. So I'm going to give you the three major ones, and this is just really for your benefit. Xy goes to, let's see, be x and then negative y. This is only useful if the reflection happens to be over the, let's see, x-axis. Let's see, we have a similar rule for the y-axis. So we have x comma y that will travel to negative x comma y. And just like the other one, this is actually only true if and only if, and that's just if and only if, that's a common abbreviation. If it's going to be a reflection over y-axis. And the last thing, last common rule I should say, is x comma y goes to, oops, sorry, drop my stylus, goes to y comma x. And this is only applicable if and only if is the reflections over the line y equals x. Which I know some people had problems graphing that, but they thought that was maybe a point or something, which is weird. This is just the same thing as like y equals 1x plus 0. So it's actually a line. And so those algebraic rules are fine and dandy, but they're only fine and dandy if you are, I don't know why it's not refocusing for you guys. It's only going to be helpful if you happen to be reflecting over these three lines, which in a second, hopefully, or maybe now even, you're seeing why that's extremely limited. But let me show you some examples of what I mean. So if I have, let's say, these points are a collection of points. Let's call this one A, and let's say this one's called B. I don't know why I put a prime there. And let's say C is right here. So if you take the first one, and let's say I want my line of reflection to be this guy, I can just feed into since I'm reflecting over the x-axis, which is this guy right here, I can just go x negative y, which means keep the same x value but flip the y value. So if this one is at 1 comma negative 1, I'm flipping over the red line. This should be 1 comma 1. So keep the x, flip the y. Next we see prime. Let's say A here is at 3 comma negative 2. Keep the x, flip the y. So now that should be at 3, 2. And then let's see B is at 2 comma negative 4. Keep the x, flip the y. So that's going to be at 2, 4. Okay, so like I said, this is really, really arbitrary because that rule that I followed, which is this guy up here, this xy goes to x negative y, it only applied if I'm flipping off the x-axis or flipping the x-axis. Which if you're thinking about it, like that's not really going to be good for us because, well, what if I'm not going to be reflecting over that axis? Like what if I have no discernible axes at all? Or what if I'm like away from the axis? So I want you guys to kind of think about this a different way. which is I'm just kind of flipping over a line. Like, so it doesn't really matter which line I flip over, as long as I'm flipping over some line, because in the end, the x-axis is just a line for us to flip. Wow, that got out of control, didn't it? So the x-axis is a line of reflection for us. So there's something really special about it. Man, I don't know what's tripping out here. And there's nothing really special about that. That kind of leads us to kind of a different ways to note this, because if all I really care about is that I'm flipping over the x-axis, that's really all I have to. I'm sorry, flipping over line of reflection. That's all I really have to note. So in addition to like the algebraic rule, there's a couple other ways we can note a reflection. Come on, Notability, you can do it. Or just because I have like 300 notes in here. So in addition to the algebraic rule, we do have a formal translation rule. I'm sorry, a formal transformation rule. So just like with translations, we do have a way to kind of note this. So that little guy right here is called a rho. It's a Greek letter. It looks like a funny looking P. So if you think about like this reflection, the only important part to really track is this line of reflection. And so over here in our formal translation rule, or transformation rule, excuse me, that's what we're going to note. So this little symbol stands for reflection. And then right below, we're going to note the line of reflection, or line of symmetry. Okay, that's going to take our point xy to our new image point x prime, y prime. And so if I'm looking at this example on the right, even though I am using the x-axis, I can still write this in a formal reflection rule. So like the example I'd be looking at would be something like the reflection over the line, in this case y equals 0, of all the points x, y, should go to my new points x prime, y prime. The alternative way, instead of actually naming the equation of the line, you can just pick out a couple points on the line. So I can say the reflection over the line that goes to the points 3 comma 0 and 4 comma 0, because those would just be like 2 points on this red line here and here. Over one a little bit actually, right here and right here. So I can just name a couple points on that line, and that's good enough to identify where that line is. Okay. And then the same thing for all the points x, y going to x prime, y prime. Just like with translations, there is a slightly more generic way to name this. So the generic rule. And again, noting that the important part is actually line of reflection, I can use a big T, and then same thing, y equals 0. Sorry, y equals 0 would mean the translation over that line, or transformation of that line. In this case, it's assumed to be a reflection, or I could say the transformation, in this case, a reflection that goes to the points, or for the line that goes to the points 3, 0, and 4, 0. Okay, and we'll see that in action. So if you're not quite sure how that looks in action, like don't worry about that right now. We'll see an example in a minute. But I just want to show you that these are 3 ways that we can note kind of this thing that's happening on the right. They all mean the same exact thing. In fact, let me copy and paste this over here. So I could use the formal translation rule. Okay, I can describe what's happening over here using this algebraic rule. I can also use any of these formal rules to describe the same thing. And just in case we weren't sure, when I say like that y equals 0, that's the actual equation of this line, which is the same thing as saying the line goes to those points, because those points occur on the line right here and right there. And then in the slightly more generic rule, y equals 0, that's still going to be this line. And then again, 3 and 4, 0 will just be points on that line. So those are all different ways to note a reflection that's happening. Those aren't terribly important though. So even though you guys probably just took a ton of notes and some of it was kind of confusing, Please know that none of that is really all that important. And the reason being is because, like, when you think about a reflection, at least in my mind, the structural identity of a reflection makes more sense. Like, in other words, like what's happening when I do reflect something. So let's talk about this whole idea of the perpendicular bisector. So let's start back at the grid. So if I wanted to identify or perform a reflection, to me it's much more important to understand like the structural thing that's happening. With a translation, it's very close to algebra, so I'm looking just if the rule makes sense, but reflections that's a little bit different. So to shed light on what I mean, let's do a quick example again. I'm not going to use points this time. I'm just going to point values. Excuse me. I'm just going to use some generic points here, but I'm not going to quantify them. So let's say I have these 3 points, and let's say I do want to reflect over this axis, this line of symmetry. It doesn't really matter, but I want to reflect over that line. Well, as you guys identified, the big idea here is that you always have a perpendicular bisector, meaning that if I take this point here and I reflect it over this line, it should end up the same distance away and in the same line, perpendicular and bisected. So what I mean is if I take the pre-image and the image and I connect them with a line, that should be at a right angle with my line of reflection, and it should be the same distance apart. So same thing, say with this guy right here. If I want to reflect it over this orange line, it's got to be 3 away from the orange line and directly on the other side as my original point. Now you can verify all this with a rule, but in the end, the structure, like I said, I think makes a little bit more sense. So the red line has now been perpendicularly bisected by the black reflection line, highlighted in orange. Same thing with this guy here. So if I want to reflect it, I got to be 1, 2, 3, 4 units on the other side of this. 4. And that's how I know I have my reflection. If you kind of look at the resulting shapes, this confirms what we kind of knew before, at least suspected, that if I do perform a reflection in this manner, the shape that I end up with should be the same exact, as it should be an exact copy. But again, this is all sans the rule, meaning without the rule. So this perpendicular bisector business, to me, is probably the more important part of this. Because that means like if I want to perform a reflection, I just have to kind of visualize this line, and it'll give me a good sense of where this thing should end up. So even if I don't remember the rule, I should still be okay. Let me give you an example what I mean. Let's take away the axis, let's take away all that stuff, and let's just pick out 3 points. So let's say pick a point here, pick a point here, pick a point here, and then let's pick a line of reflection. So just to make it tough, let's make it right there. So it's not up and down, it's not left and right. So if I want to perform this reflection or at least map out like how you would, you still have to keep this identity of the perpendicular bisector alive. So if I want to reflect this orange point, I'd have to come into this line at a 90-degree angle, and I'd have to go the same distance out from that. So if I take this point, same idea, I'd have to come in at a 90-degree angle, and then I have to leave it at a 90-degree angle the same amount. Now this is all a sketch, of course. I'm not doing this perfectly, because we said a sketch would suffice now just to kind of get a good idea for us. But this is, like I said, this is a part of the reflection piece I think is more important, that you're keeping this perpendicular bisector piece alive and well. Now this isn't perfect, of course, but the idea is that is actually what's needed in a reflection. So like the important part of a reflection is this idea that the pre-image and the image have to form a perpendicular bisector. Okay, and so you can certainly see that when the axis is line of reflection, but it should occur pretty much anywhere. So like if I were to take like this line, and kind of turn it, like that perpendicular bisector, no matter what, should be present, whether it's straight up and down, whether it's directly left and right, or whether I'm at an angle. Now this isn't perfect because I sketched it, but you can kind of get the idea that this line of reflection being a perpendicular bisector is the most important piece of this. So if you're making notes here, that is my line of reflection, which is just the same thing as saying like a line of symmetry. They actually mean the same things. So even though we have all these rules to kind of have this idea in our head or kind of note it, which are important, these are okay to memorize if you want to. They're not really that important though. The real important part is understanding that with a line of reflection, you always have this perpendicular bisection business. Because if you don't, well, you simply don't have a reflection. Okay, so like it's a two-part condition. Um, but when you think about the rule and its kind of rigidity, or you consider this perpendicular bisector, again, it leads us to one really important point, which is that if I'm so concerned with keeping like the same distance and making sure the points are aligned one on top of the other, that means we can conclude that oh, come on. That reflections have to be rigid motions. Which, unless you didn't watch the last video, this term rigid motion can mean a couple different things. Rigid motion can also mean congruency transform. Which is just another fancy way of saying okay, so whatever shape is put into a reflection is the same shape you get out of it. So I kind of use an example of um, like getting into a taxi cab and going to a different part of town for a translation. This would be like the equivalent of being like in one of those Six Flags rides that takes you and kind of flips you really quick to like the other side. I could think of like the Yankee Clipper ship being kind of a good example of this, kind of moving back and forth. So it's important to note here that reflections aren't changing anything. Like it's not something that you like you can put like a circle into and get a square or anything like that. Like you put a circle into it, it's just going to reflect it, flip it over to some other place, but it's still going to remain the exact same circle. Now to back that up, we can again review this idea of perpendicular bisection. So like this literally took like this yellow triangle, and because it's perpendicular, it's directly across, which means it's not reoriented, and because it's bisected, it's the exact same distance away. And so that's what I mean when I say rigid. It's not changing anything. We see that in the rule also. Um, and I think the groups did like a really eloquent job explaining this. But if you think about like xy to yx, like those are the same distances. X to negative x is the same distance. It's just the opposite direction. Y to negative y, same thing. So like there's no numbers involved here. So there's no dilation. There's no blowing up or shrinking. It's just kind of moved to the opposite place because in the end that's all negative really means, just like the opposite. So that's really all I have to say about reflections. You get the rule, you get the perpendicular bisector. Like that's the most important part I think to remember about reflections. That if I take a point and I take its reflected point, that should form a line that's perpendicularly bisected by the line of reflection. Like this always has to be true, otherwise a reflection just didn't happen. Which leads us to think, that leads us to believe now that these are rigid motions, which means they don't change anything. Um, so next part for you is of course the reflection part. I'm sorry, the summary part. Do this now. Tie these into your notes. Again, my advice is just like, what if someone texted you and say, "Hey, tell me everything you know about reflections." To do that well, you'd have to review the vocabulary, which is why I say the first thing you do is reread and highlight important parts. And then if you're highlighting them, and again, if you put it in your mind as context of texting your friend, you have to use the highlighted words. Okay, and then of course, if you post this to Edmodo, that's gonna be worth some points for you in the end. And you know the thing about using highlighted words is because again, if you're trying to talk about reflections and you're not using words like perpendicular bisector or rule or line of reflection, like that is really going to be not a good summary for us, right? So like if you're looking at this and you don't tell your friend like this stands for a line of reflection, and or you're saying this is just 2 points on the line of reflection. Then you're just not doing a good job with the summary. Also, please don't forget about the questions. But that's what we'll have to say about reflections. Again, you're gonna have some stuff to do in Khan Academy. Here's a quick example of something that you would possibly see. This question says arrange the vertices of the yellow movable thing after there was a reflection across the x-axis. So the first thing you have to kind of do is realize, or at least kind of note, like where this line of reflection is. And so, in the best possible way you can with a mouse pad, like that's my line of reflection. And so you could totally go to the rule if you wanted to. I don't think you need to here, because again, you have this. Hopefully, you have this idea in your head that if I'm going to be pulling a reflection, I gotta like show a perpendicular bisector. So if I take like this point, let's kind of move out of the way. If I take like this point A and I go directly to the line of reflection, okay, it's got to go directly towards it, so it's a right angle. And then if you notice the units, that's 1, 2, 3, 4, 5. That means wherever I put my point has to be 1, 2, 3, 4, 5 units away, and also in the same line because it needs to be perpendicular as well. And so that will tell me that this point has to go right here. Boom. Okay, rough right there. You know, Khan Academy, it's got to be exact. And same has got to be true for all my points. So like if I look at, whoa, that one got way out of control. Okay, so look at W, and I think about W to a straight line to the line of reflection, which is the x-axis. It's got to be right angle, of course, and it's 7 units away, so that means like this point has to also be at 7 units. Same has got to be true for K, so that was, what, 4 units away at a right angle, so its new value has to be 4 units away as well. H is 3 units away, so that's got to be 3 units. So I can really do a good job of like mapping out where my points have to be before I even do anything with them. And it's like that one's got to be, let's see, this guy's got to be here, 7. This one has to be, oh, do you want that? Got to be there. And this guy has got to be up here. Okay, so they're all perpendicular. They're all the same distance away. So if I check my answer, hopefully I did it right. There you go. So it's all about this perpendicular bisector. I can't say anything more about perpendicular bisector beyond that. Okay, so that's how you have to handle these reflections. There is a variation that is going to appear randomly where it asks you to actually like physically move a line around. But again, just please note that like the controls are intuitive, but in the end, you want to move it around in a way that'll produce a perpendicular bisector, right? See if we got lucky and get that one. Nope, we didn't. This is the translation one, as you can see by the vector notation. So that's what I have about reflections. This is another couple videos coming. Sorry about the long-windedness, but you know sometimes how I am. All right, thank you guys. I'll see you later.